Hi everyone, so if we want to find the vector equation of a line in 3D space, the first thing we're going to need is some information about that line. Now, you know from the very first parts of A-level maths in the topic coordinate geometry that there are several ways of finding the equation of a line, but you need at minimum two pieces of information. Two known points on a line, knowledge of a parallel line and a point, or any kind of combination that would allow you to create those things. It's exactly the same for 3D points and therefore vector equations of points in 3D space. Here in this problem I have points A and B relative to a fixed origin O, and I think this is the most general way of calculating one of these problems, and we can extend into other topics or ways of calculating things if you like, so parallel lines and all that kind of stuff from this. Okay, so at the moment all I've got are 2 points A and B relative to this fixed origin. I have no vectors yet, but I can create two vectors quite quickly. I can create the vector OA, and OA, which we could call A in this case, would be the vector 1, 2, 3, and I'm using columns because I don't want to write loads of extra i's, j's and k's. I can do the same with the vector OB, which would be, we could call of course B as well, it's quite helpful, smaller notation, and that would be 2, 7, 6. Now, what I would be asked in a problem like this would be the vector equation of the line through A and B, so the line that passes through both of those points. Now notice that's not doing anything anywhere near O, but O is our fixed origin. It allows us to place our line in space, and that's really handy. So knowing how we get to our line from the origin can be quite useful to us. Having the vectors A and B now also allows me to work out the vector A to B, which is effectively the little line segment in between A and B. Now, from your study of vectors at A level, hopefully you know that that is effectively going from A back to O and then O out to B. So that would be the vector minus A plus B, which in this case is 1, 5, 3. Now that's great. That's done a line segment. It's done that short piece deliberately combined between A and B, but doesn't do the infinite line that goes on in either direction. Now, any other point on this line we could get to by doing a multiple of this vector 1, 5, 3, because that would say if this is vector 1, 5, 3, that could get us to the next point, which is another 1, 5, 3 up the line. Now we know that doing multiples of things, that gives us parallel situations. So in fact, lambda, or any multiple, you could use, P, S, Q, whatever you like, but we tend to use Greek letters here for these sorts of things. This says it's a multiple of the vector 1, 5, 3. Now that would generate a parallel line anywhere in space that's parallel to the line segment AB. So notice all I've done here is I have taken my direction vector, as we know these are called, and created a general parallel direction vector. So we're good. We have our line segment AB, we've got this chunk of space here, and now we've extended it so it's an infinite line going in either direction, but we've run into a slight problem because this lambda 153 could describe this red line that I've just drawn here, or the blue line down here, as long as it's parallel to my original line segment AB. How do I make it sit exactly on the line going through A and B? Well, much like with a traditional line, we have the option of pinning it onto a known point. Now we've got two known points. We know point A and point B, but we know them relative to a fixed origin, and that's actually the helpful thing here. So what I want to do is fix my line in space. And I would do that saying it's this far away from O. Well, I've got two ways of saying that. I can either say that it is the vector 1, 2, 3 away from O, or the vector 2, 7, 6. This has now created any point that lies on that line, and this is the notation we use. We use the notation R for a vector. So a random point on the line can be found by using the vector 1, 2, 3 to get to the line, and then any multiple of, or whatever necessary multiple of, the vector 1, 5, 3. Notice this does have some strange parallels to what we understand by the equation of a line. Y equals mx plus c, where c in the straight line version, of course, is the y-intercept, but is also a known point on the line. And we have this kind of multiple of our gradient. So our direction vector, this 1, 5, 3, don't forget that is a direction vector, acts like our gradient. It tells us where to go, much like a gradient does. So a gradient says for every 1 you go along on the x-axis, you go up 4, for instance. That would be a gradient of 4. Here, we're doing that in multi-dimensional space. So what this direction vector is saying is for every 1 you go up, along on the x, you go up on the y by 3 and out on z by, up on y by 5 and out on z by 3. It's doing exactly the same thing here. And then what we've done is we've created a known point that we know lies on the exact line we want, and that, of course, is one of our position vectors. So to generalise then, our vector equation of a line, R, is notated with A, our position vector, plus lambda lots of B, our direction vector. So just to make a note of that, where A is a position vector, so that is from the origin to a known point on the line, and B is our direction vector. And that could be the vector in between 2 points we know lies on the line, but because it's acting like the gradient, if we have been given a parallel line, we know that it has the same direction vector. So this could be the vector between 2 points, or it could be parallel to another line. And we take the direction vector from that bit. And that's our vector equation of a line in 3D space. Now, of course, like I've been sort of making gentle references to, we actually like having Cartesian forms. So that's in terms of x, y, and would be now z, instead of this r and lambda thing. So let's take our vector equation and we'll get to our Cartesian equation. All right, r represents a general point on the line, so I'm going to use x, y, and z here. I've got to get them in somewhere. That makes a good point. That's a general point on a line. It has an x, a y, and a z location. And of course, don't forget this is a vector here. This is the position vector of that general point. We start with our known point or our known location on the line, and we get there by using the vector, the position vector, go A1 out on x, A2 up on y, and A3 out on z, and then lambda lots of our direction vector. So that would be us moving up and down the line. That would allow me now to say, well, x then is A1 plus lambda lots of B1. Y is A2 plus lambda lots of B2, and Z is A3 plus lambda lots of B3, just by effectively equating each individual line as it goes along. Now, all of these equations, these are beginning to look a little bit more Cartesian. We've got x's and y's and z's, but we've got this lambda. So we need to rearrange this now to get rid of lambda. So I'll write each equation in terms of lambda equals something. So lambda is x minus a1 over b1. It's also y minus a2 over b2. And it's also z minus a3 over b3. Well, that now, because I have 3 statements that all equal lambda, that necessarily means that they all equal each other in this situation. So that means that x minus a1 over b1 equals y minus a2 over b2 equals z minus a3 over b3. And that is the Cartesian equation of a line in 3D space. In the next video, we will look at some examples using these equations.